All right, I think it's recording. Yeah. Uh, so we talked about generally some history of robotics. I told you some highlights about robotics in fiction, robotics in industry. I want to be more focused on more modern, I would say, robotics today in terms of scope. Just a little bit talking about robotics today, because what we talked about, we basically ended the conversation at Unimation, right? Unimation Incorporation. That was basically, it was in uh, end of 50s and 60s and then 70s that basically became popular robot arms that they I would say came into picture mainly as laborers, right? Replacing workers doing mundane tasks, some things that probably we don't want to do, or it's much cheaper to automate that. So that was basically where we start, where we ended our conversation. Now, let's be more close to what's going on nowadays in robotics, right? More close to modern day. So just we can think about it as robotics today. Now, if I want to classify the types of robots that you see nowadays, or basically the machines that you see that fits into kind of definition of robots, I would say we kind of have two generations of robots, right? There is this the, the first generation of robots that are fixed, right? They're fixed in one place, very similar to that robot arm that was developed first time by the Unimation Corporation, right? Uh, those are very basic ones. They are used for automobile manufacturing, electronic device manufacturing. They're used for material handling, right? You can use them for uh, the main application. Actually, I believe that the first application for that robot arm developed by Unimation was in GM to basically do some die casting or getting the parts out of the cast after during the die casting process. So material handling could be a very good example of that generation, like the generation of robots that are fixed, arms that are fixed. They are used to move boxes in manufacturing environments. They're used to move things from conveyor belts from one place to another. So that's where you mainly see that generation of robots that we basically refer to them as the first generation of robots. Now, very obviously practical. There is an estimation about more than 1 million of them are at work, like at least up until a couple years ago. And yeah, these are the descendant of what was developed by Unimation. Now, they perform some kind of an endless loop of typically pick something up and then pick that thing from location A, drop it at location B. And again, the main feature of these robots, this first generation, is that they are fixed at the location. Right. Let me at least put some notes there. So you can put it under robots today. I don't know. I saw the title somewhere, so you can use that. And put it under first generation. First generation, I guess. Now, I'll call that, let's use manufacturing. Robots. It's typically used in manufacturing environment. Now, can say they perform typically, it's probably better to go ahead. They typically perform an endless loop of uh, picking up things from one location and dropping or putting, oh, different, wrong color, and putting them in another location. Pretty general definition. Now, the feature for these robots, as I said, that's why they call it the first generation, or the reason they call it the first generation is that they are fixed, right? They are fixed at a location. That's the main reason we call them first generation. Now, as I said, automobile industry, electronic device manufacturing, material handling, depending on where you look at, you'll see these robots. Mainly, you see them as arms, pretty much, moving things from one place to another. They're good. They do, again, they're descendants of the robots developed by Unimation. So, still practical, very common in manufacturing environment. You see probably the most common picture you've seen this generation of robots in automobile manufacturing lines, that they do welding, they do assembling, they move things around. Now, that's pretty much the focus of this course, right? We look at not even the whole thing. We just look at, and the scope of the course is that we just look at mainly kinematics of these types of robots, these robot arms, as we call them. We look at path planning. How can we actually define a path for some given robot with specific dimensions or length for the arm or different parts of the arm? How can we define, sorry, how can we design a path to take something we want, because that's what typically happens. You want to take something from one place and put it in the other place. So you have to define a path. How do you want that robot to go from one place to location A to location B, from location A to location B? Now, there is this, obviously, the next generation as well, as simple as that. They just call them next generation of robots. Now, the main difference between that generation and the first generation is that they're able to move. So instead of that fixed robot that you had, now you have robots that they can move. So let me just put it under second generation or next generation. They don't really say next generation of robots. They're not really named. I just call them first. We call them first generation and next generation. So let me call next generation of robots. So again, the main difference is that they can move. The most famous, I would say, well, probably not the most famous, depending on what field you work in, but the one that a lot of you have seen is those little vacuum cleaner robots that move around in a room, and basically they do the vacuum cleaning for you in whatever space they are left alone, I would say. They were introduced around 2004, and again, up until a couple of years ago, more than 10 million of them were sold. So pretty common because they are kind of cheap, right? They're popular because they perform a very popular task like cleaning, right? And they are cheap, so you can just buy them basically. And the reason they're cheap because they have very limited computational capacity. You can't really do that much there is not that much calculation going on. Those robots don't actually know. A vacuum cleaner, those kind of vacuum cleaners, they don't know where they are in a room, right? It just yes.
Sorry to cut you off. I have a question.
Yeah, go ahead.
So, like, where is the line between a machine and a robot? So, like, is a vacuum considered a robot? This is-
Uh,
As I'm saying this, it sounds kind of ridiculous.
no. That's so we are going to define a robot in a little bit. But generally speaking, we call something a robot. Let's put it this way: if there is a machine that moves things from point A to point B, we call it a robot. If there is a machine that moves from point A to point B, we also call that a robot. You can just go with that definition. So if you want to put both together, you can say a robot is basically just a goal-oriented machine. Right? It's a more elaborate definition. A goal-oriented machine that can sense, plan, and act. Three main actions for a robot. That way you can distinguish. Oh, I'll give you a definition, I guess, at the end of this part. But that's pretty much how you can separate a machine from a robot. Right? So are CNC machines robots? Maybe that could be a good question. They fall in the boundary. They really are not robots. You can program them. They do function, so they fit in the category, right? So it's like a machine that can do something. It's goal oriented, right? You can program them and they act. They plan based on the program. They act. But they have some sensing, so it fits in the category of robot, right? If you go with the definition. So I would say that's the limit. Right? You have a machine. I don't know if it makes sense what I'm trying to say, but uh, we can always go with that definition. Look at something. Is it goal oriented, meaning that can move from one place to another, or I can move something, right? Something from one place to another. Can it sense, plan, and act based on that sensing and planning? Then it's a robot.
Thank you, Professor.
Yeah, of course. But yeah, that's actually a good question. That's something hopefully we get at the end of this section to get a little bit of better sense of what is a robot and what fits into that category. All right, so next generation, as I said, let me just put a few words here. So they can, or let's say they are able to move within the environment. Right? That's the main difference between this generation and the previous generation. Now, so I said the vacuum cleaners would be a good example. Let's put it, maybe we can put it here. Vacuum cleaner robots. Just keep in mind that these vacuum cleaners don't really have a good sense of where they are. So they move around kind of blindly a little bit. They have sensors. They detect if they hit something. They change the direction, but usually they move in a straight line, right? They suck up the dirt, and then if it hits something, they just bounce off and move in a different direction. They just keep going around until they don't really have a specific, I would say, design to make sure that they cover the whole area in a optimal time. It's just they move around and keep sucking up the dirt, and that's the reason they're cheap, because the computation is very limited. Now, another example of that would be if you go to a port, right? There are some ports that actually are automated now. That there are large size robots, I would say, that they pick up containers from location A. They usually put them on these, I would say, kind of transport style robots. They put them on them and they move the container from location A to location B, or as long as they're programmed to do that. The new version of that would be, I don't know if you've seen those videos of Amazon warehouses, that there are some those small robots that they can actually carry boxes and packages within the warehouse from one location to another. It's not just Amazon, I guess other companies do that. But it's becoming more common, obviously, because they're cheap to build. They don't need that much of programming and computation. Cheap labor that works the typical thing that we like about robots. They do some mundane tasks that is basically can be done 24/7 as long as they are doing the task instead of a labor, right? These are the examples. Let me see if I can also put it here. Transportation robots at ports, small robots moving packages in warehouses. These are a couple of simple, the simple ones. I think I actually set aside a video for the one in the port. This one. You don't need to watch the whole thing. I just want to give you a sense of what I'm talking about when I talk about big size. Share sound.
And these high-tech Titans' output is staggering. Each loading crane can deadlift 40 tons. Below, the container's chariot awaits. Called an Automated Guided Vehicle, AGV, this car has a mind of its own. Literally. There's no driver because an onboard navigation system regulates its position, direction, even speed by a magnetic grid set into the tarmac. Once the container is loaded on the AGV's back...
All right, you got the idea. Again, I'm sure you've seen those videos about small ones in warehouses that have become more common nowadays. Now, these are the simple ones. Right? Now, we can go further and look at the more complicated ones. As a matter of fact, the one that, again, maybe a lot of you have seen, robots developed by Boston Dynamics, right? It's more of a fun thing even nowadays to look at those videos of that dog that they developed, the robot that is very good at handling itself, very good at controlling and staying balanced under different movement and different environments. As far as I know, I think they're pretty common now that they even sell it. So if you have I do have a video of that too, just to the side. Spot, they call it. If you have, $75,000 sitting around, you don't need it, you can buy one, as far as I know. Anyway.
Can you let that video just go all the way through?
Sure.
Robots are now helping healthcare workers at Brigham and Women's.
There you go. That was not an advertisement, but again, as you said, they're available. You can buy one as a pet. All right, so that's more like a more modern version, right? So let me just put it here just to complete the list. Um, Boston Dynamics. I would say dog. I used to call it little dog and big dog. Now it goes with the name of Spot. There's one version, right? This is the next generation, as I said. They can move. Right? It starts from small vacuum cleaner, goes up to these Boston Dynamics robots, and even go further. You can think about let's you know what? Let's be more organized. So let's say this generation of robots. Let's say can. I'll just give you the classification. The group that are moving on wheels, right? Like the vacuum cleaner ones. The class that are moving with legs, right? It's not by any means a complete list, but just some of them, some classification. So Boston Dynamics, dog, and also there are a couple more. They can the group that they can fly. All right, let's can fly, which unmanned vehicles fit in this category, right? The famous one is I guess at least the older version, or much more nowadays. You have small drones even, but big scale. You can think about Northern Group Global Hawk, right? Or the small flying one, drones. Let me just put it as drones. There's a class that they can swim. All right, depending on if you're dealing with underwater unmanned vehicle. Right? These are actually becoming more popular, and nowadays there are more research on them, along with the drones. Obviously, I don't really have a specific example name for these in mind, but you can always look them up. But this is the next generation. Right, these are the ones that they start from simple ones to go to up to very complicated ones. But what they have in common is that they can move within the environment, as opposed to the first generation that was basically just fixed in some place. So I said it would be more fun to look into those, and obviously more complicated, multidisciplinary field. There is a lot going on behind the scene: electronics, programming, mechanical engineering, electrical engineering. The programming of these robots by itself, all robots. If you know the most famous, I guess, operating system or environment that is used for programming robots is ROS. No, you may never heard about that, or you're not gonna heard or use it at all. But that's a specific environment developed as actually free and open source. But a little challenging to be comfortable with it, but that's one environment that they do programming for operating and coding robots, either first or generations or next generations can be used for any. All right, so this is the situation nowadays, right? That we haven't moved from the first generation completely. Obviously, they're still used. The new Tesla manufacturing environment they were building. I don't know if you follow the news, but a lot of what was going on was first generation robots, right? Robot arms doing everything automated, from welding to inspection to moving, everything that's going on. And the next generation of robots to move parts, or I would say any product from one place to another in the manufacturing environment. Now, if you want to define, like, let's also put a definition for robotics. Right now, definition is a little tricky because depending on who you talk to, it's going to give you a different definition. Right? How do they define a robot, or generally robots? But I'll give you this definition, which I think is the least controversial and very broad in general, that pretty much everyone can agree on that. So, definition. Now, we talked about two generations, right? We said a machine, you can say a machine that moves things from location A, or let's put A to B, from A to B, and A and B being a location, a spot, position. Or you can, depending on if you're talking about the second generation, a machine that moves from A to B. Right? Now, good, general, relatively simple, but to have one definition that covers both and pretty much every machine that fits into the definition of robots, every machine that fits in the definition of a robot, I'll define it this way: a goal-oriented machine, right? I lost the connection. All right. That, let's say, that can sense, plan, and act. All right, so start from the beginning. A goal-oriented machine. This is an important part of the definition. It has a goal. Either it's trying to move something from one place to another, or it's trying to move itself from one place to another. So can move something from one place to another. Can move from one place to another. It's goal-oriented. It has some goal in mind when it's operating. These three are also the important parts of the definition: sense, plan, and act. Three main actions of a robot. Has to be able to sense, like keep in mind, it's like a human being, like even an animal, I would say, any living being. Sense, be able to sense the environment. What sense is that, depending on what kind of robot you're planning to use, or what is the purpose of that robot, the goal that that robot has is supposed to have. The same thing can be different. Can be just a vision, can be complicated. Just can be able to touch, can be able to smell. If it's some kind of a robot that you want for gas detection, let's say, in an environment, should be able to hear. Depending on what kind of robot we're thinking here, and what is the purpose of that. Should be able to plan accordingly. If it senses some specific chemical in the air, or it smells some gas, it's supposed to be able to plan for something. So either trigger an alarm, either dial a specific number, either go and do a specific, close a specific like valve, and should be able to act. Right? Whatever the plan is, obviously it should be able to act on it. So we'll call this three main actions of, I don't know my handwriting. What's deteriorating? Three main actions of a robot. Right? That's a pretty good definition. Now, again, you will see different definitions in different references, but that's what I like. It's broad enough, gives you a sense of determining whether something can fit into the definition of a robot. All right, so far so good. Now, one thing I just want to mention before we move and start digging deeper into first generation and robot arms, that is the main, what we the focus of this course, again, this introductory course. So we define things, we look into the kinematics, how can we plan action, movements. Hopefully we get to talk a little bit about sensors and actuators. But one thing we want to just to close this conversation about robots is that we use robots for specific purposes. We use them to, as they call, dull, dirty, and dangerous. Right? These three types of tasks that we usually use robots to do. If it's dull, something that is very dull, a repetitive action that doesn't need any skill, it just needs someone who just moves one. You need someone who can move this box from here to here and then continue doing that. So dull task, we use robots. So dirty, it's dirty. Right? It's going down at the dirty, I don't know, path, like a swamp to discover something, or look, or identify the environment or detect something specific. Right? Some dirty jobs. It's pretty broad, but you can think about any job that's basically you don't want to get your hands dirty. You prefer to have a robot doing it for you. The last one is dangerous, which is I would say probably should be at the top of dull and dirty. We talked about this in the last class that when Argonne National Laboratory came up with the whole slave master robot arm because they were developing nuclear weapons, right? It was after World War II, and they needed to be able to move things around, radioactive materials, without being in that environment. So it's a dangerous task that obviously you go for replacing whatever labor you have or whatever task is being done. You go for robots to do that for you. That's a typical things that say 3Ds, dull, dirty, and dangerous. But one thing you have to add to this is also things that people cannot do. Right? Can get into the category of dangerous, but we can also put it as a different category. And by that I mean doing, let's say, operations in space, or sending or going to space, going to moon, going to a different planet. It's dangerous, or people cannot do, right? Or deep sea, right? Ocean, you want to go very deep in the ocean, some uncharted territory in the ocean that nobody has ever been, or it's very deep, no light has ever reached that environment. You can fit it into dangerous, but you can separate that as a category that things that people cannot do. So we use robots. Let me fit this into a little more organized. So let me start with this characteristics of robots. Why do we use robots? They're consistent, they're accurate, they're reliable. Three main reasons that we use robots: consistency, accuracy, reliability. So we use them because they're consistent for the most part. It's tint, accurate, and reliable. Reasons we use robots. Where do we use them? Well, as I said, I'm just going to briefly put it here so you have it in case you forget. Dirty and dull tasks, right? Example would be like boring, dull, any task you can think about. I'm not going to add something there, but as I said, like manufacturing environment is a pretty good example. Dangerous, right? Task could be dangerous. They can do things people shouldn't do. It's like unhealthy, risky environment again, and right, also radioactive material environment, or any environment that people shouldn't be there. Right? They can do it for you. And I'll add again, the third category is not really. Let me just separate them. The third category is not really. You can still put it in dirty, dull, and dangerous, but dirty, dull, dangerous. I'll just add one here. They can do things people can't do, which can include the dangerous tasks or something that's almost impossible. You want to go inside a specific, let's say a tiny pipe to inspect the pipe for any kind of crack or any kind of problem. Let's say you have an oil pipe underground, 3 inches diameter, 5 inches diameter. You want to check the pipe for 2 kilometers and see if there is any possible corrosion, crack, or something that needs attention and maintenance is required for that. That you can do. You know, there are like small robots that can send into these pipes. People can't do that, but this robot can get into the pipe and can give you a very good video or scanning of the environment, how things are, and you can just sit outside comfortably and just monitor the motion of the robot and the pipe condition. All right. So this pretty much closes this topic I wanted to talk about. Right? Some definition, what are the characteristics of a robot? Hopefully by now you have a sense of the field. Obviously not a very good, still detailed understanding of what's going on. It's a broad field, but I just wanted to give you a general view of what is going on, where are we going, what is this course what is it going to focus on? As I said, we're going to focus on first generation of robots, very straightforward, simple ones, relatively simple ones. I should mention that. For robot arms, right? That's it. And we'll look into the kinematics and how they work, the parts, I forgot the term for that, the terminology, the things that we need to know. All right. Now let's talk about. I'm going to start. So now I'm going to start talking about arms. Right? But well, actually, what I'm going to tell you right now can fit both in arm for robotic arms and any general robot. So we're still, I guess, in the scope of general definition for the course. Now, I just want to give you again a general sense of components of a robot. As I said, it's a multidisciplinary field. We defined what the robot is, but now we want to get a sense of what are the general components of a robot. So let me just give you a bunch of general definitions you probably can find in different sources, but for the sake of completeness, since again it's an introductory course here, we just have to make sure that we cover the bases before we move forward and get into more detailed stuff related to robotics. Now, if I want to start looking at the components in a simple way, first thing that comes to mind in a robot, whether it's a robot arm or it's a moving robot, can be a Boston Dynamic dog, can be a drone, it's a link. What is a link? Well, you probably know what the link is from courses you had from before. But if you want to define it, it's basically a rigid body that forms the robot. So we'll just As simple as that. Let me put it there. First thing I mention is a link. And I simply just define it as individual rigid bodies that form a robot. But if you look at the robot arm, a simple robot arm moving things from one place to another, it has multiple links. Right? If you think about that, this is fixed to ground, and this is just the gripper. It's just picking something, moving somewhere else. It's formed by multiple links. Like one link there, link here, a couple of links in the gripper. As simple as that. Just you can also think about the link as a rigid member that can have a relative motion with respect to other links, right? In a robot arm, there's a rigid link that can move with respect to the other links. That's another way of thinking about the link. You can just think about it that way. Second one, maybe I should use this type of link. I'll use this. Second one, naturally we go from link to joint. Now joint is pretty much what connects two links. Right? Any two links are connected by a joint. Right now we're going to talk about different types of joint, but that's a general definition, the general idea of what a joint is. So, two links are connected by a joint. Can add more to it probably. Let me see what I put here. Something better. Well, let's put this where their relative motion can be represented by a single coordinate. Very formal version of that. And the coordinate that you use to define the joint, to define that relative motion, kind of determines what kind of joint you're dealing with. Right? No, we have we can classify the joints into 7 types of joints. Right? Yeah, 7. So let's go with that. First type, and the first and second was the most important one, and the ones that we're going to be focused on this course, because pretty much any industrial robot that we are going to deal with, their motions you can describe using just these 2 first joints. So these are the most important, most common type of joints that you'd see. Any other joint, one way or another, any other motion, one way or another, can be represented by these 2 joints. Obviously, a series of them in different directions, but these are the types of joints that are most common ones. So the first one is a revolute joint. Revolute joint, which should use R. The second one is prismatic joint. Prismatic joint, or P. Now, revolute joint, as I said, the coordinate that you use to define the relative motion between links defines your joint. So the revolute joint, the joint coordinate for revolute joint is an angle. Right. Let me just put it here and then I bring it. Maybe I can do it right now. I have some pictures of joints just to make sure that things are clear. So I used to give these pictures as handouts, but since now we're doing online, I'll post the notes. I apologize if I drop them here, and then if you're taking notes, it's just a huge thing to draw. You can just leave it empty and later on look at the notes. Remember where they are. So revolute joint, right? The joint coordinate that basically is the characteristic of this joint is an angle. And that angle would be this revolution, right, around this axis. So for a revolute joint, you have a joint. The axis for this joint passes through, and then the motion is around that axis. So let me put it this way. Joint coordinate is an angle. What does that mean? It means you can define the motion of a revolute joint using an angle, depending on how much you rotate around the axis. So if you think of this as a revolute joint, we typically represent that with kind of a cylindrical shape like this. This is the axis. And this is the axis of the joint. These are important because we're going to use these axes to define different types of configurations or configuration of robots. So if you have a revolute joint, as I said, we typically represent them with a cylinder symbol. It can rotate either clockwise or counterclockwise, depending on which direction you look at, around this axis. So if my thumb is the axis of this revolute joint, 4 fingers, if you go depending on clockwise or counterclockwise, as long as you rotate around the axis, right? You have your axis, you can rotate either direction. And the angle, the motion is represented by the amount that you're rotating. So if you remember degree of freedom, minimum number of coordinates that we use to define a motion, this has 1 degree of freedom, meaning that there is the only possibility is to rotate around the axis of the joint. And the axis is passing through. Prismatic joint, as I put there, is pretty much just, you can think about it as straight line motion, right? The joint coordinate is translation. So the joint coordinate for the first one is angle, or you can think about it as rotation. The joint coordinate for the prismatic is translation. Let's put it this way. So this is represented by joint coordinate is translation. I'm not going to draw it, but it's pretty straightforward. We have let's say 2 links connected to each other here with a prismatic joint. So this is one link. This is another link. They're sliding. There's a translation. The relative displacement between 2 links is a translation. Now, where is the axis for prismatic joint? Here is the axis. Oops, that's not what I wanted to. I guess I'm going to end up drawing it. If you think about this as a prismatic joint, if I speed up the process, there you go. So prismatic joint, we typically represent that with a kind of box instead of a cylinder. So this is, if this is a prismatic joint, right, as represented here. The axis is right here. Axis. So the motion is along or collinear with the axis. It's along the axis. We have a translation like this instead of that rotation that for revolute joint that we had a rotation around the axis. I emphasize on axes because, as I said, we use the relationship or the way the axes of these joints stand to define different configurations of robots. So these are the most important ones. And these are the ones that we're going to be focused on this course. Everything we define we define using these two joints, revolute joint and prismatic joint. Now I'll show you the other ones. You will see them, but you'll see later on that we kind of represent every joint as a combination of the first two, any motion that we have. So the third one, as I already brought here, is the helical joint. Let's see. Helical, or I didn't use joint word for it. Let's just keep it that way. Helical or screw joint. All right, you can see how the motion is. There is a revolution, right? There is a rotation, and there is a translation. So if you want to replace this joint with revolute and prismatic joint, there's going to be one revolute joint and one prismatic. You can replace the helical joint with that. You can represent that with that. Not replace it, represent it. When you're doing, when you're analyzing the motion of part of a robot. A couple more. I don't know if I can fit the other one. I did a pretty bad job space management here. Three more. I just mentioned them for the sake of having them here. I'm sorry, it's a little unorganized here. So fourth one is the cylindrical joint. Cylindrical joint represented usually with C. Again, helical joint represented with H. Cylindrical joint, again, you can represent that with revolute and a prismatic joint, but there is no constraint. So in helical joint, there is a constraint that the amount that you can move, there is a relationship, right? It's again, if you remember degree of freedom, it's 1 degree of freedom because the two motions are related for helical joint. Right? You can't go up freely without rotating, whereas in cylindrical joint you can easily do that. So it's a combination of a revolute and a prismatic joint. Keep going, the same story. We can just, I'm going to list them there again. We don't really spherical joint, spherical. I probably should follow the same order that I brought them here. So let's go with universal joint, universal, which typically they show that with U. Then the sixth one would be spherical, which they typically represent that with S. And the last one that I did not even bring it here, but it's a still pretty common one, is a planar joint. Now, planar joint, imagine two plates on top of each other. One can rotate with respect to the other one, and can move. So you have 2 degrees in X and Y direction, and then you have rotation. Right? That's a planar joint. You can define the relative motion between two links using the planar joint. Now, planar joint, if you want to think about that, is basically 2 translation and 1 revolute. So 2 prismatic, right? You can achieve that motion using 2 prismatic and 1 revolute. So any of these motions, not that you can replace these joints, you still have to use these joints when you build a robot or when you're making a robot. But any of these joints, when it comes to analytical studying the motion, can be represented by a bunch of revolute and prismatic joints. That's why we only focus on those 2. So don't make things complicated. Those 2 are good enough. They do what we want. And you'll see we represent pretty much all the typical industrial robot arms using those 2 joints. All right, so length, joints. Right, we can go faster now. The third important part, or the components of a robot, is I was not using this color, right? Is the manipulator. So I don't remember, was I using, yeah, black. So there we go. Sorry for jumping back and forth. Manipulator. Now, manipulator is basically the main body of a robot. It includes links, joints, and other structural elements together. Example would be the wrist, gripper, control system. Manipulator includes all of that. Manipulator becomes a robot when it's with wrist, gripper, and control system. Wrist, gripper, and control system are not part of manipulator. Manipulator, it includes only links, joints, and some other structural elements. Let's say when you're connecting two joints, you're welding an extra piece of metal there, or you're fixing something there. Whatever structural element, you put an extra, create an extra hollow somewhere to put electronic there later on. All these structural elements together with, including links and joints, they're called it's called manipulator. Now, if you talk about wrist, gripper, and control system, manipulator becomes a robot. So, manipulator, the main body of a robot. That's pretty much it. It includes the links, joints, and other structural elements. So I said a manipulator becomes a robot once you have a wrist there, gripper connected to that using the wrist, and then you have a control system that can actually control your robot arm or industrial robot. That becomes a robot. But manipulator, so far, is I would say the main structure of your robot, if you want to think about that. The fourth one is the wrist. Now, wrist is a type of joint. It's a joint that connects the, you can think about, if you think of a robot arm, typical industrial robot, you can think about a pick and place robot, picking something from somewhere and putting it somewhere else. Wrist connects the arm, or this part of forearm as they call it, when you think about an arm, and the end effector. Right? End effector, what is an end effector? That's what I'm going to call define next. But wrist pretty much that's what it does. So we're going from manipulator, which includes the whole structure. We need a wrist to connect the manipulator to the rest of the structure. To connect the end effector to the rest of the structure. So that's what wrist does. We'll talk about wrists and how to assemble them in one or two classes further during this semester. But simply put, wrist is just basically a joint that connects the forearm, or just arm, and the end effector. What is end effector? Again, I'll get into it, but pretty much that's the part that performs the function that we need. Now, if you have a robot arm that is supposed to do welding, end effector would be a piece that does the welding. If you have an arm that is supposed to pick something and place it somewhere else, end effector would be a gripper, as they call it. Pick it and place it somewhere. Think about the manufacturing lab, the robot arm we have there, and all of you took that course, that lab. That's pretty much a simple thing that you can keep in mind when we are talking about different parts. So the wrist is where the gripper, the end part, is connected to forearm. Now, the wrist can be a spherical joint. I said it's a joint. It can be a spherical joint. So spherical joint can be represented with 3 revolute joint. If you think about the spherical, we can have motion in every revolution around each axis. This way, right? This way, and this way. So we have revolution around each axis. Let's just put it here. and how much of this is going to stick. So there, these, let's put it this way: the rest can be more simple ones, right? Can be just 2 revolute ones. Doesn't have to be exactly a spherical joint. Thinking about 3 revolute joints, can be just 2, can be just 1, depending on what is the function of that robot arm is. Right? So wrist can be a spherical joint, in parentheses, represented by 3R joints that are, I'll get into this when we talk about wrist. Let's not make it complicated. All right. Basically, there are 3 revolute joints that the axes intersect, right, at the common point. And that's why they call it, that common point is important. That's why it becomes a wrist. But we'll get into details of a wrist later on in this semester. The important part in terms of the functionality of the robot is the end effector. So end effector. That's the part that is mounted on the last link, right? You have the wrist, and the end effector is mounted on the rest of your, let's say, manipulator to do the job that this arm is supposed to do. So I'll put it this way: the part, it is the,
I would call it the part that interacts with the environment.
that's true. You can call it that way. It's the part that interacts with the environment. It's a good approach to call it. All right, so is the part mounted on the last link to do the required task. I can add that to this, or let's say the part that interacts with the environment. It's a very good way of putting. A simple types are a gripper, just can pick something, place it somewhere else. So the whole combination of a wrist and an end effector is just called hand. Typical normal way of, I guess, in human being. So if you see somewhere they refer to hand is basically just wrist plus the end effector, whatever that end effector is. If it's doing the pick and place, if it's doing the welding, if it's sucking the part and take the part and move it somewhere else. Moving is not always pick and place. Or if it's pushing some, it's simply just a prismatic joint pushing the boxes off a conveyor belt. Now, in order to move things, we need something that can move different links. That's basically falls into actuators. Actuators, you can think about them as muscles of your robot. They are the ones that they derive or they make the motions happen. So 6 would be actuators. Defining it, I would say they derive, these are the drivers, right? They act as the muscle of a robot. They can change the configuration. So moving from one place to another, you need an actuator to actually make that motion happen. Yeah. So,
excuse me, Professor, did I say actuators?
Yes, it's actuators.
Okay.
Yeah, my handwriting, depending on how things are going, actuators. So they act as the muscles of a robot to change the configuration. Basically make the motion happen. It's you know, they provide power. The power needs to be strong enough to overcome some external force, like when you're picking something. Obviously, there are a lot of calculations go into this. Right? It has to overcome the gravity to picking that piece up. It has to be power, has to be, or the actuator should provide enough power to overcome the inertia of the link that is connected to. Good amount of calculations go there to figure out the amount of power that should be provided to the actuator to make the motion happen. Seventh, I would say, important component is sensor. Your robot should be able to sense. Right? Whatever that sense could be, as simple as being able to make sure that it's in touch with the part that is supposed to, let's say, supposed to do welding on, or it can be more complicated, like a moving robot that has some vision system that should be actually be able to see and process the let's say objects around, may create a map of where it is and locate, should be able to locate itself with respect to other objects to navigate its path toward a specific goal. So from a very simple to a very complicated task, you need sensors to be able to or at least your robot is able to function. Right? So sensors. You can think about them as parts or components for detecting whatever is going on around, collecting information about the environment, whether it's internal environment or external environment. Right? Internal environment, external environment would be what is around. Internal environment would be position, velocity, acceleration of a specific link. So you need sensors for both. So I want to put it more general form. The elements used for detecting and collecting information. That's how you write information. Collecting information about internal, let's say, and external state, better to say, an external environment. Environmental states. I'm going to fix it this way. Environmental states, such as position, velocity, acceleration, force. Now, remember, this position, velocity, acceleration can be the velocity of one link with respect to other, or position of one link with respect to other, so you can control where your robot should go and where it is and where it should go and how fast it should go. Or it can be the position velocity of the whole system, how fast it's moving in the environment, right? The positioning of objects around. So sensors have a wide range of tasks, in robotics, tasks that have to accomplish depending on what they're used for. Because sensors are the ones that can be used to control the system, and they tell us where each link is. So the controller is capable of the processing for path planning, let's say, or it's capable of path planning, figuring out where the link is, where it should go, so how much power it should give to a specific actuator to guide that link or part of the robot to that specific position or location. The last one, just very briefly put it here just to complete this list, is, as I said, is a controller. Right? Very important part, obviously, the brain, kind of. The controller unit, you can think about this unit, has three main jobs. Information is supposed to get the information from the sensors and process them. Because the information, raw information, doesn't have any meaning. It has to get the video, sound, smell from the sensors and do the processing. So what is this sound? What is this video? Is it an object that we have to avoid, or if it's the object that we are supposed to go and grab? So one main job it does is related to information. The other one is decision. Once the information is processed, the controller unit is supposed to plan the motion. So if this is the object I'm supposed to pick, or this is the object I'm supposed to avoid, right? What is the decision? If it's something I want to pick, let's make a plan for that. If it's something I'm supposed to avoid, make a plan for that. And then finally, communication. Right? So communication between the sensors and actuators. So once you make a plan from the data you got from sensors, you have to send a signal to actuators to make that motion happen. So it's more like a brain of your system. I'll just put it like this: information in terms of processing the information, decision making process that happens there, and then communication. So the main three jobs of the controller. So all these together, you can think about this as components of a robot. Very general form. Now, we talk about link, joint, manipulator in general, wrist, and effectors. We may or may not get a chance to talk about sensors and actuators a little bit. Definitely, we're not going to talk about controller. That's a whole story. If you take control course, actually, that's where you might see a lot about how to control a stepper motor, let's say, as an actuator. How can you control that for a specific motion, like its velocity and acceleration, or the position it can create in a specific link or arm. All right, I'm going to stop here.